All right, let's dive right into this explainer. Think of me as your personal physics tutor, and we are going to make sure you absolutely ace that upcoming exam on wave mechanics. Whether you're cramming for a final or just trying to wrap your head around how energy actually moves through the universe, you're in the right place. We're going to break down all these complexities so you can easily visualize the concepts and the formulas you need to know.
Here is our syllabus for today's session. We're going to cover wave types in history, transverse versus longitudinal, formulas for wave math, calculating wave speed, superposition and interference, and finally, reflection at boundaries.
So let's start with Section 1, Wave Types and History, from the 17th century to quantum mechanics. Getting this broad classification right is literally step 1 for any physics test.
There's a fundamental difference between the two main types of classical waves. Mechanical waves, they absolutely need a physical material, a medium, like a string, water, or even the air you're breathing right now, to travel through. Because of that, their speed completely depends on the properties of that medium. But then you have electromagnetic waves. These are the rule breakers. They don't need any medium at all. They can just zip through the pure vacuum of space at the universal speed limit, the speed of light.
Now, this wasn't all discovered overnight. Our modern understanding traces way back to the 1600s. We had absolute heavyweights like Christian Huygens studying wave motion physics, Robert Hooke looking into elastic media, and Isaac Newton laying the groundwork for speed of sound formulas. They really built the foundation that we're still using today.
Moving right along to Section 2, Transverse versus Longitudinal Visualizing Wave Behaviors. Let's really zoom in on those mechanical waves, the ones that need a medium, and look at exactly how they move through that material.
The completely crucial point here is directionality. Transverse waves are all about moving perpendicular to the wave's path. Imagine plucking a guitar string, right? The wave travels horizontally down the neck, but the string itself is actually moving up and down. Longitudinal waves, on the other hand, push and pull in the exact same direction they're heading. Think of sound moving through a pipe. The air molecules are compressing and expanding perfectly parallel to the path of the sound.
Listen, if you memorize just one thing today, make it this. A wave is a moving disturbance that transports energy, not the physical matter itself. The medium just oscillates in place. It's the energy and the information that are actually taking the journey.
To really make this stick, let's use a couple of visual analogies. Think of a piece of cork just bobbing in a pond. When you drop a pebble, the ripples move outward, but that cork just goes straight up and down. The water isn't flowing away, the wave is. Or think about a stationary train. When the engine gives a sudden jolt, that jolt is transmitted all the way down through the spring couplings from car to car. The energy travels the entire length of the train, but the whole train didn't suddenly jump bodily down the tracks.
Okay, Section 3, Formulas for Wave Math, the vocabulary of oscillation. Let's get into the math because before we can calculate a single thing, we absolutely must master the vocabulary.
Our first crucial term is wavelength, represented by the Greek letter lambda. This is our spatial measurement. It's literally how physically long a single wave cycle is in space. If you were to just freeze time and measure the minimum distance between 2 points having the exact same phase, like from the very top of one crest to the exact top of the next consecutive crest, boom, you have your wavelength.
Now, while wavelength is about physical space, period, represented by capital T, is our temporal or time measurement. Pick a single point on a string. How long does it take for that exact element of the medium to complete one full oscillation, go all the way up, all the way down, and get right back to its starting point? That block of time is 1 period.
And finally, we have frequency, denoted by the Greek letter nu. If period asks, how much time does one cycle take, frequency asks, how many of those complete oscillations happen in a single second. Because of this, frequency is simply the mathematical inverse of the period, just 1 divided by t. And we usually measure this in hertz. All right, Section 4, Calculating Wave Speed, featuring tension, density, and Newton's mistake. Armed with our new vocab, we can tackle a classic exam problem, figuring out exactly how fast a wave is moving.
So, to find the speed of a transverse wave on a string, you just follow these specific steps. First, identify the restoring force, like the tension in the stretched string. Second, identify the inertial property, which is the linear mass density. Third, divide that tension by the mass density. And fourth, just take the square root of that result to get your wave speed. The huge takeaway here? The speed relies entirely on the string's physical properties, how tight it is and how heavy it is, not the wave's frequency. You can wiggle that string as fast or as slow as you want. The wave speed down the line stays exactly the same.
Now here's the answer to a classic trick question you'll probably see. Because sound travels as a longitudinal wave, you'd think it travels fastest in light, airy gases, right? Well, actually, no. Liquids and solids are much more difficult to compress than gases. They possess a vastly higher bulk modulus, which is basically elasticity. That massive increase in bulk modulus easily overrides their higher mass densities. Because of this, sound actually rockets through solids and liquids way faster than it does through a gas. And hey, if you're ever struggling with these formulas, take comfort in this. Even Isaac Newton made mistakes. Newton incorrectly assumed sound pressure changes in air were isothermal, meaning the temperature stayed perfectly constant. He calculated a speed that was way off. A scientist named Laplace had to correct his homework later, proving that these are actually rapid adiabatic changes. Factoring in Laplace's correction gave us the real, accurate speed of sound.
Moving to Section 5, superposition and interference, when waves collide. We know how single waves travel, but the real world is messy, right? So let's look at what happens when waves actually interact.
Think about this. What happens when two wave pulses traveling in opposite directions cross each other in the exact same medium? Do they bounce off each other? Do they destroy each other entirely? Or do they just pass right through?
The answer lies in the principle of superposition. When waves overlap, the net displacement at any given point is literally just the algebraic sum of the displacements from each individual wave pulse. So they pass right through each other, but for that brief moment they overlap, you just mathematically add their heights together. And this perfectly explains two absolutely critical real-world phenomena. When waves are perfectly in phase, crest overlapping with crest, their amplitudes add together, creating a resultant wave with a much larger maximum displacement. That's constructive interference. Two quiet sounds can suddenly combine to be super loud. But when waves are completely out of phase, their positive and negative displacements cancel each other out entirely, resulting in zero net displacement. That's destructive interference. This exact math is how your noise-canceling headphones create perfect silence.
All right, our final section today, Section 6, reflection at boundaries, rigid versus open ends. Let's examine what happens when a wave completes its journey and reaches the physical end of its medium.
The type of boundary really changes everything. If you have a rigid boundary, like a solid wall, the wave reflects back, but it suffers a phase change of pi, or 180 degrees. It flips completely upside down, because the boundary cannot move. But if it hits an open boundary that is completely free to move, the wave reflects back with absolutely no phase change. It stays perfectly upright.
So, we can easily calculate these mechanical and electromagnetic waves. But I want to leave you with a really fascinating question as you continue your physics journey. How do the bizarre matter waves of quantum mechanics challenge our very perception of reality? The electrons and protons that make up your own body behave a whole lot like the waves we just studied. Let that sink in and let it challenge how you see the universe until our next explainer. You're going to absolutely crush this exam.